our next subtopic in our waves unit is 5.2, periodic wave phenomena. And by observing two types of mechanical waves, transverse waves and longitudinal waves, we can really discover some characteristics and behavior of waves depending on the conditions they're under. And we're going to start diving into some of these different phenomena today. Before we jump into the different phenomena, it's important to know what a wavefront is. And a wavefront can be defined as all points on a wave that comprise a wavefront. So two successive crests would be examples of wave fronts. Now, one way to visualize this, if you have a water-filled sink and you were to slowly drip water out of a faucet into that sink or tank, the expanding ripples would be examples of wavefronts. As those ripples move out, they stick together. If you've ever had a really still pond or pool and you've thrown a rock or some sort of object into there, you can see the ripples travel outward, and all of those points on the particular wavefront are in phase with each other. So it's going to be important to know what a wavefront is before we move on. And one thing that is helpful also is to know that these wavefronts are in phase. And we talked a little bit about that last week, but now we're going on to different things. And the first one we're going to dive into is Doppler effect. And this can be defined as when a source or an observer, a receiver of waves are moving relative to each other, the observed frequency is different from the frequency of the vibrating source. Now, this change in observed or apparent frequency due to the relative motion of source and observer is called the Doppler effect. And you may have seen this in earth science, and we'll get into that in a little bit. Okay, so now we're going to make some diagrams to dive into the Doppler effect and help us kind of visualize it. So on the left, I am going to draw a stationary source. And on the right, I'm going to draw a source moving at a constant velocity away from one observer and toward another. And I'm going to pause the video to make these drawings and then talk you through it. Okay, and here are my two drawings. Feel free to pause the video if you need to copy these down. So on the left, we have a stationary source, and in the middle here is just some source. Maybe it's emitting some sort of sound waves or music or anything with noise. And if it's not moving, whether we're on the left side of the wavefronts where observer A is or the right side where observer B is, both of these are going to perceive a normal frequency and a normal wavelength. And the same goes for observer A. But when we go over to observer or example B, here we have some source that's moving at a constant velocity, as you can tell by these dots that are equidistant. It's moving towards C and away from observer D. Now you can see here that the wavefronts are closer together, and over here they're spread more apart. And this causes the apparent change in frequency, even though, let's say here it's emitting 500 hertz. It's still emitting that 500 hertz, but now these observers are going to kind of perceive or observe it differently. Now, C will observe, since you can see these lines closer together, a shorter wavelength. And as you learned in the simulator lab, a shorter wavelength means a higher frequency. And at D, these wavefronts are spread apart more. So observer D is going to observe a longer wavelength and a lower frequency. Even though the source is going to emit a constant frequency, they will observe different things. And one example you may see of this, if you were standing on the side of the road and a police car is driving towards you at a constant velocity, as that siren is approaching you, you are going to hear a higher frequency. And then as soon as it passes you and moves away from you, you are now going to hear the pitch of the siren change, and it's going to be a lower frequency. So for sound waves, frequency is directly related to pitch. There are some real-world applications of the Doppler effect. In earth science, you may have seen it in weather forecasting. And when we're talking about outer space and galaxies moving towards us or away from us, they can observe those using a redshift and a blue shift, which we'll learn about the different frequencies of light waves in a few weeks. And it also can be seen in police work, specifically with radar guns. And when a policeman is, pointing a radar gun at your vehicle, they're using that frequency. If you are driving too quickly, that sound will reflect and bounce back towards them. So they actually use the Doppler effect to investigate that. Okay, our next wave phenomena that we're going to investigate is interference. And before we get into that, we're going to define superposition. Often you'll hear the word superpose, but superposition can be defined as when two or more waves travel through the same medium simultaneously. And it is true that, really infinite amount of waves can interfere. We are only going to focus on two at a time. And the principle of superposition states that the resultant displacement at any point is the algebraic sum of the displacements of individual waves. And this is going to be known as interference. And we're going to look at two types of interference. So the first type of interference will be constructive interference. And when I hear the word constructive, I think build. So this is going to cause an antinode, which is where the maximum displacement, so we're building it up, the maximum displacement of a medium when two waves are interacting. And constructive interference is when the wave displacements of two in-phase waves in the same medium are in the same direction. Now, let's say here we have a wave pulse moving to the right, and over here we have a wave pulse moving to the left, and let's say the crest is 1 meter. Well, when these two waves pass through each other or superpose this wave pulse, they will add up and constructively interfere. So when the two pulses pass through each other and cause constructive interference, we add them up. So if we go back to the definition, it is that algebraic sum. So here, since they're both positive, we're going to add them up. Now, destructive interference is when two waves of equal frequency and amplitude have a phase difference of 180 degrees meet at a point or superpose. And destructive interference produces things called nodes. Now, let's do that same example. Let's say here we have a crest, but if we remember, out of phase means half a wavelength apart, which would be this distance. So here, let's say this is again 1 meter, and say this is moving to the right. And over here we have a trough, and let's say it's 1 meter, and this is moving to the left. When these two pulses pass through each other, they are going to completely cancel out or destructively interfere. Now, one thing to add is after two wave pulses pass through each other, it's as if nothing ever happened. So after they pass through each other, this one will continue moving to the left, and this will continue moving to the right. But while they pass through each other, they will destructively interfere. And this is important because next week when we have this next segment, we're going to look at standing waves. Here's an example of standing wave. And so this would be one wave where there's no displacement. This is going to be where a node happens, and at points where there is a maximum, that's going to be where an antinode occurs.